Last time, we had our first look at Isaac Newton's magnificent theory of mechanics, including his three laws of motion and his law of universal gravitation. Newton shows that the familiar force of gravity, the force that makes the apple fall from the tree, is also the force that steers the planets and moons in their orbits. He's able to derive Kepler's laws of planetary motion as consequences of his theory. The same force, the same physics applies both on Earth and in the heavens. It's a great theory, but is it right? And how do we apply it to the real world? Let's begin with one of the equations that we wrote down last time. Suppose an object is at a distance r from the center of a mass m. This might be an apple near the surface of the Earth or a planet far from the sun. Anyway, the object experiences a gravitational force which causes it to accelerate. And what is that acceleration? We found that A equals g times m over r squared, where g is Newton's constant, a constant parameter of nature, like the speed of light or the mass of the electron. G has a very small value, which means that gravity is a very weak force. Notice once again that this acceleration A does not depend on the mass of the apple or the planet or any of its properties. The same object would accelerate the same in the same place, any object at all, if it were at the same distance r from the same mass m. Newton had this all figured out about 1666. So let's put ourselves back in the 17th century. Suppose Newton has just shared with us his brand new theory about gravity. It's obviously a clever idea. But what difficulties would we notice? For a start, if we want to apply this law to a planet orbiting the sun, then we need to know r, the distance from the sun to the planet. But in 1666, nobody knew what that distance was. The size of the solar system was just guesswork. To make matters worse, nobody knew the mass of m of the sun, or the value of Newton's constant g. So we have a beautiful formula for the acceleration of gravity, but we literally know none of the variables or constants on the other side of that equals sign. Some theory. Finally, Newton's theory predicts that everything responds to gravity with the same acceleration. That's certainly what Galileo concluded from his own simple experiments. But is this really true? And how do we know? That's how things would look in 1666. To overcome these difficulties, astronomers and physicists had to conduct the most careful observations and the most delicate experiments ever performed. It was not easy. In fact, it took more than 2 centuries for all of these questions to be firmly settled. It's quite a story. First of all, let's talk about distance. How do we determine the distances between the planets and the sun? Well, it turns out we can determine the ratios of distances with some fairly straightforward observations. Copernicus himself knew how to do this. He worked out that the orbit of Mars is about 1.52 times larger than the Earth's orbit. And the radius of the Earth's orbit, as you recall, is known as 1 astronomical unit, or AU. The orbit of Mars, therefore, has a semi-major axis of 1.52 AU. The orbit of Venus, on the other hand, is only 0.72 AU. And so on for all the planets we can see. So we can measure all of the orbits in AUs. But how big is our yardstick? How far is the sun from the Earth? That distance, nobody knew. Now, the astronomers of antiquity had made some progress. The Greek Eratosthenes had determined the size of the Earth pretty closely. And another Greek astronomer, Aristarchus, worked out the distance to the moon. His method combined information from solar and lunar eclipses, and it worked out nicely. Aristarchus had a second method to determine the distance to the sun, but the sun is a lot further away than the moon, and his method gave poor results. His guess at the Earth-Sun distance was only 5% of the real value. Other astronomers trying the same technique got very different numbers. And all their results were worthless. So matters stood until 1672, while Newton was still fooling around with his gravitational ideas on his own. Over in Paris, a French astronomer named Giovanni Cassini set up a very clever observation to really determine the size of the astronomical unit. Now, I've called Cassini a French astronomer, but the name Giovanni Cassini does not sound very French. In fact, he was Italian by birth and began his career in Italy. Then in 1669, the French king Louis XIV invited him to come to France to help with the building of a new observatory. Cassini loved it in France. He agreed to stay on as the director of the Paris Observatory. He became thoroughly French. Cassini was an immensely talented observer. He was a pioneer in using the telescope to make very accurate measurements in the heavens. He had discovered several moons of Saturn and also noticed a division within Saturn's rings, something we will have occasion to remember later on in Lecture 10. Though Cassini himself was always quite cautious about interpreting his observations, the observations themselves were first-rate. So in the early fall of 1672, the planet Mars came comparatively close to the Earth. Every couple of years, Earth and Mars are on the same side of the Sun. So that's a time when you can get a really good look at the red planet. The approach of 1672 was unusually good. Mars was not only near the Earth, it was also near the point on its orbit closest to the Sun. Some of you might remember that this also happened in the year 2003. That meant that Mars would be especially close to the Earth. So Cassini set about determining how far away Mars was from the Earth in September of 1672. And to do this, he had to make simultaneous measurements of the position of Mars in the sky from two different locations on the Earth. So he dispatched an assistant, Jean Richet, to a French colony on an island off South America. Cassini and Richet had to be extremely careful and precise. The observed difference in the position from the 2 points was less than 1/100th of a degree. But when Richet returned to Paris the next year, Cassini could combine the two measurements together, along with the exact distance between the two observation points, and figure out the distance to Mars. And once that single distance is known, all the other distances in the solar system follow. So what Cassini and Richet did was to establish that basic yardstick for all our measurements of distance beyond the Earth. Of course, more precise measurements have been made since then, of course, but theirs was the first one that was worth anything. And today, we know that the value of the AU, the size of the Earth's orbit, 1 AU, equals 1.5 times 10 to the 11th meters, which is about 150 million kilometers. Okay, now we know how to measure distances. But how about the other variables in our gravitational equation? How do we determine the mass of the Earth, m, or the mass of the Sun? How do we determine the gravitational constant, g? The two questions are actually related. If we can answer one, we can answer both. Because here, near the surface of the Earth, the value of r is about 6,400 kilometers. That's the radius of the Earth. And we can measure the acceleration of gravity, and we find that it's about 10 meters per second squared. So, if we knew the value of g, we could solve the equation and determine the mass m. And we could do something similar to find the mass of the Sun by observing the accelerations of the planets as they swing around in their orbits. Newton himself never did this. He never learned either the value of g or the value of m for the Sun or the planets. But he could know, and did know, the value of the product g times m. And it turns out that the combination g times m is what usually appears in the equations. So Newton never found out just how strong the gravitational attraction was. He never found out the mass of any astronomical object. But in the end, he didn't have to. Only the product G times M mattered for the calculations that he did. But that does leave a rather huge unanswered question. Newton claimed that every object exerts an attractive force on every other object, and the strength of this universal force is determined by the value of G. It's one of the fundamental parameters of nature. Wouldn't it be a good idea to measure it? What would we have to do to measure G, Newton's constant? Well, we'd have to take a pair of masses in our laboratory, known masses, so many kilograms, and put them a known distance apart. And then we'd have to measure the extraordinarily tiny gravitational force between them. How small a force is it? If we have two 1 kilogram masses 10 centimeters apart, the attractive force between them is only a few billionths of a Newton. It seems impossible. But that experiment is exactly the experiment that was done in 1798 by the brilliant and eccentric English scientist Henry Cavendish. He made the first real determination of the value of G, Newton's constant. It's one of the most wonderful experiments ever performed. I call Cavendish an eccentric because he was. He was one of the richest men in England. He more or less lived in a castle, and he was absolutely obsessed with science. He was probably the most meticulous experimental scientist of his day. He was a man with a real flair for inventing new ways to measure the world. Cavendish discovered the element hydrogen, and he worked out the composition of air. He made a great many discoveries in the new science of electricity. But Cavendish was a true recluse. He shunned most visitors. He even had his own library moved to a different house so that visitors could consult it without bothering him. His discoveries were communicated to the world via the Royal Society of London. But many of his discoveries, like the pioneering work he did in electricity, were not published till years after his death. So what did Cavendish do? I've set up an apparatus here to show you. It's called a torsional balance. That's an idea that Cavendish borrowed from the geologist John Mitchell. And so hanging from a very thin fish line, you might not even be able to see it, is we have a horizontal rod with two masses mounted on the ends. It's sort of like a hanging dumbbell. And the hanging dumbbell can turn freely one way or the other. And even a very tiny force can cause it to turn a little bit. And that makes the thin line get a little twisted, which causes it to resist further turning. Now, we also have a couple of large masses. And in our case, we're using standard brass shot puts like you might find at a track meet. And these shot puts exert tiny gravitational forces to the masses that are at the ends of the dumbbell. So, if we put the shot puts just so, and you have to be very careful, put the shot puts just so, then the gravitational force can cause the dumbbell to turn a little bit. Then, if we take them away, the line relaxes and untwists. So measuring how much gravitational force twists the line, and by doing some other experiments to figure out how much force produces how much twist, we can find out how big the gravitational force is. That's how it works. Of course, Cavendish's apparatus was very different from this. His dumbbell rod was actually 6 feet long. And instead of shot puts, he used big spheres made of lead. They weighed hundreds of pounds. And he had to eliminate air currents and other things that might disturb the experiment. So what did he do? Well, he put it all out in a shed on his property, which wouldn't be disturbed, and he shut everything up in a box with only a couple of small holes in the box so he could see into it. And he had to devise a way to measure the very slight angle that the dumbbell turns. And the way he did it is he mounted a mirror on the dumbbell, and then by looking at the way light bounced off the mirror, he could measure that angle very precisely. Now, we have some advantages over Cavendish. He suspended his apparatus with a metal wire. We are using this single filament fish line, which twists much more easily, and that means that the observed effects of gravity over time can be that much clearer. But we still must take very careful steps to eliminate all of the other forces that might be acting. Let me tell you a little bit about my own experience working with this apparatus in the lab. First of all, we had to eliminate air currents completely. And so we shut off all the air conditioning vents in the laboratory, and we put the entire apparatus in a plexiglass box. That meant that we had to somehow devise a method of moving the shot puts from outside the box, and we had to move the shot puts extremely slowly so that they didn't generate air currents of their own. We had a little trouble with a very large mass, a big table next to the apparatus, which actually had a gravitational effect. It was actually a tidal effect, as we'll see in Lecture 8. Now, the worst were the electric forces. Remember, the electromagnetic force is extremely large compared to the gravitational force. And so any net static electric charge in the apparatus would completely overwhelm the gravitational attraction. Cavendish actually anticipated all this. He had done those electromagnetic experiments that wouldn't be recognized for many years. He would have known about that, and he did it right. So let me show you a time-lapse video of one of my early runs with this apparatus. You can see in this video, which takes one frame every 10 seconds, the force of attraction between the masses and the shot puts. But if you work out the numbers, that force is a little bit too strong. It's not just gravity. So probably a significant part of the force here is the electrostatic force. All right. So what if we do this right? What if we do the experiment and we eliminate all the forces and the air currents and everything? How fast is the gravitational acceleration that we would see in the apparatus? Well, it turns out that in about 15 minutes, the ends of the dumbbell will move about 2 centimeters toward the shot puts. So gravity is a very weak force, but it is not too weak for us to comprehend. 2 objects that you could hold in your hand could produce a displacement that you could see with your eyes over a period of time that you can understand. The law of universal gravitation is really true, even for such small objects. And if we do this experiment carefully enough, we can determine the value of g. Modern experiments give this value for the gravitational constant. G equals 6.67 times 10 to the minus 11th meters cubed per kilogram second squared. Once we know this number, Newton's constant, we can determine the mass of the Earth, as we described before. And that is what Cavendish did. So we often say that Henry Cavendish was the man who weighed the Earth. But he did a lot more than that. He weighed almost everything. Most of the things in the universe, the moons and planets and stars and galaxies, are too far away and too big for us to bring them into our lab and measure their masses directly. The only way we can determine the mass of one of these objects is by observing its gravitational effect on other nearby objects. Knowing the strength of the gravitational force, in other words, knowing the value of Newton's constant g, we can deduce the mass. And it's all thanks to Cavendish and his dumbbell. Finally, I want to turn to the last experimental question I mentioned at the beginning of the lecture. This is the fact, first noticed by Galileo, that all objects fall with the same acceleration. But in Newton's theory, that fact arises in a funny way. It all depends on the idea of mass. And the mass of an object, let's think about an apple again, plays two different roles in Newtonian mechanics. The first role played by mass is as a measure of the apple's inertia, that is, its resistance to changes in velocity. We can call that inertial mass. It's the mass we find in Newton's second law. The net force equals mass times acceleration. But the apple's mass also plays a role in the formula for the gravitational force on the apple. That is to say, the mass of the apple determines how strongly the gravity of the Earth pulls at it. So we can call this role gravitational mass. The point is that inertial mass and gravitational mass are always exactly the same. And this fact is sometimes called the principle of equivalence, the exact equivalence of inertial and gravitational mass. Because of that, we can just cancel the mass out of our equations. We find that everything in our lab should fall with the same acceleration, just as Galileo observed. But when we state it like that, it seems almost like a coincidence. Why should inertial mass always be equal to gravitational mass? In Newton's theory, there does not appear to be any real reason for it. It's just one of those things that happens to be true. Or is it? Are inertial and gravitational mass always exactly the same for all objects, no matter what they're made of, no matter what the circumstances? Do all objects really fall with exactly the same acceleration? As a matter of fact, this principle of equivalence is a unique feature of gravity. Other forces of nature simply do not have this property. Let's discuss an example. About 100 years after Newton, the French physicist Charles-Augustin de Coulomb figured out the law governing the electric force between two charges. His equation looks a lot like Newton's law of gravity. That is, the force between charges Q1 and Q2 is given by the equation F equals K times Q1 times Q2 over R squared, where K is a constant expressing the strength of the electric force. The electric force does not depend on the mass of an object. It depends on the electric charge, which is an entirely independent property. Two particles with the same charge might have different masses. Two particles with the same mass might have different charges. So if you set up a big static charge somewhere and study how other charges are accelerated by it, you would not find that they all accelerated in the same way. Some would be accelerated quickly, some more slowly. Positive charges would be accelerated one way, negative charges the opposite way. Neutral particles would not be accelerated at all. Gravity, on the other hand, is strange and unique. Everything is accelerated by gravitational forces in exactly the same way. Galileo did his experiment by dropping masses side by side, and he found that any differences in acceleration were very small, and he attributed those differences to air resistance, friction, and so on. Newton himself did some better experiments using pendulums made of different material, and he found that the principle of equivalence held good to about 1 part in 1,000. But such an important and unique feature of gravity needs a really solid experimental basis. And that basis was provided by a series of amazingly precise experiments carried out between 1885 and 1910 by Baron Laurent Eötvös and his assistants. Eötvös was a Hungarian nobleman and a professor of physics at the university in Budapest. Indeed, that university is now named for Eötvös. He was also a famous mountaineer. He was the first person to climb some of the more difficult peaks in the Italian Dolomites. One of the peaks there is also named for him. Eötvös loved a challenge, both in mountain climbing and in science. The essence of Eötvös's experiment is absurdly simple to state. Like Cavendish, he used a torsion balance. Eötvös dispensed with the big outside masses and made the two masses at the ends of the dumbbell out of different material. Iron and brass, say, or glass and wood. He let the balance come to rest, and then he just watched it very closely. Of course, the gravitation of the Earth affects both ends according to their gravitational masses. And as the Earth turns on its axis, both masses move in circular paths around the Earth. And they resist that acceleration according to their inertial masses. Now, in Newton's theory, where gravitational and inertial masses are equivalent, these effects work out just the same for the two masses. So there would be no net effect on the torsion balance. It would just sit there. But suppose the principle of equivalence is not exactly true. Suppose the objects on the two ends have slightly different ratios between their gravitational and their inertial properties. Then as the Earth rotates, the two ends of the dumbbell will respond slightly differently. There will be a tiny waggle back and forth in the torsional pendulum once each day. Eötvös designed and built a series of more and more sensitive torsional balances. He coped with a lot of experimental headaches. For instance, the slightest daily temperature variation between one side and the other might completely hide the effect he was looking for. But in the end, his experiments allowed him to conclude that the principle of equivalence, the equality of gravitational and inertial mass, was true to better than 1 part in 100 million. Nowadays, with great improvements in technology, we can push that precision to 1 part in 100 billion. That's interesting and important for a lot of reasons. It means that Galileo was right, really, exactly right, as far as we can tell, when he said that everything falls at the same rate. This was one of Galileo's crucial discoveries back in Lecture 2, you'll recall. And as we will see in Lecture 14, the principle of equivalence, so strikingly confirmed by Eötvös, later became the cornerstone of Albert Einstein's astonishing new theory of gravity. And Eötvös's experiments were amazing accomplishments in themselves. They are justly famous even now as supreme examples of the art of experimental physics. Physics has many beautiful theories, many startling and wonderful ideas, but all of that is built upon a foundation of observation and experiment. Without data, we're just guessing. An astronomical observation or a laboratory experiment is a way of getting Mother Nature herself to answer some question. How far is the sun? How strong is gravity? Do different objects really fall with exactly the same acceleration? And once nature responds, her answers must guide all our thinking. But it's time to go back and have a deeper look at Newtonian mechanics, the theory based on Newton's laws of motion and universal gravitation as formulated in the Principia. For the next several lectures, we'll dig deeper into those laws, deeper even than Newton himself went in his own lifetime. We'll also see how the force of gravity shapes pretty much everything in the universe. So, the world of Newton's Principia, starting next time. I'll see you then.